Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
So, good morning, good afternoon, good evening to everyone, and a very welcome to the final event of the 2024 ITU GeoAI Challenge, which is now in its third edition. So this is a very exciting event. I believe the most exciting event of the year for the GeoAI, because we are presenting the winners of the challenges. The ITU GeoAI Challenge aims to provide a platform for collaboratively addressing real-world geospatial problems by applying artificial intelligence, machine learning to advance the United Nations Sustainable Development Goals. Today's session will feature the presentation of the best solutions for the three problem statements that were proposed. So, GeoAI Challenge for Agricultural Plastic Cover Mapping with Satellite Imagery, which was curated by FAO, so the Food and Agriculture Organization of the United Nations. The GeoAI Challenge for Clandestine Runways Detection in the Peruvian Amazonian Basin with open source satellite, curated by the United Nations Office on Drugs and Crime, UNODC. And finally, the GeoAI Ground Level NO2 Estimation Challenge, which was curated by Politecnico di Milano, the Department of Civil and Environmental Engineering, and University of Padua, the Interdepartmental Research Center in Geomatics, CIRGEO. The top three teams for each challenge will showcase today their solutions and will be awarded during this session, receiving money prizes and certificates to recognize their outstanding performance. So I'm pleased to notice the high level of participation for this year's challenge. Specifically, the ground level NO2 estimation challenge had 799 enrolled with 372 active competitors. This shows the real interest in GeoAI for advancing the SDGs, so we are very happy and we thank all the participants to these challenges. Okay, but without further ado, let's move now to the first challenge. So let me call now Peng-Shu Hao from FAO, who will lead the session on agricultural plastic cover mapping with satellite imagery. He will make introductory remarks and then will invite the top three teams to describe their solution. This session will last 25 minutes. Peng-Shu, the floor is yours, but before giving you the floor, I want to remind everyone that, first of all, Peng-Shu, you have 4 minutes for the presentation of the challenge, and then each group has 7 minutes. So I will be very strict with the timing, otherwise we won't be able to give everyone a chance to speak and reach the awards ceremony. So now really, Peng, the floor is yours.
Okay. Thank you, Malia, for your introduction. So let me share my screen. Okay, hello everyone. My name is Peng Hao from FAO of United Nations, and for us, the topic of the GeoAI challenge is to map the agricultural plastic cover using satellite imageries. The work is led by UN OpenGIS initiatives and also FAO and ITU. So here is the challenge that we have this challenge. The target is to use satellite images to identify the agricultural plastic covers, which is an important facility used for agricultural applications. And basically, there are two kinds of agricultural plastic covers. One is temporal agricultural plastic cover, and the other is permanent agricultural plastic covers. So in this challenge, we provide data and ask all the participants to use satellite images and the training data we have provided to identify these agricultural facilities. And we have selected three test regions, one in Spain, the other in Kenya, and the third one located in Vietnam of Asia. And all these test regions have plenty regions of plastic covers. And for this challenge, this is the timeline, and we have provided the bi-weekly satellite images for each test regions, and also we provide training and validation samples for the participants. The participants will use the satellite the training samples to extract the spectral and the temporal information from the satellite imagery and use this information to train their classifiers. And the automatic validation sample is conducted by the validation samples we have provided, which is available in the Zindi platform. And also, we ask the participants to conduct the bi-weekly plastic cover mapping using the model they have trained. And in total, by the deadline of November 11th, we have received 76 submissions in total. And from all these submissions, we selected the top 10 for the second round evaluation. And after that, we have selected the top 3 based on the materials they have submitted and our evaluation for their novelties and their overall performance. So now is all for my talk, and then we will give the floor to the top participants that we are planning to prize. So Stephen, are you here? Maybe we can from your solution.
Yeah, sure.
Okay.
Could you, okay. Can you see my screen?
Yes, go ahead.
Cool. So my name is Stephen. I'm going to present the first list solution for plastic cover detection. I want to go deep into the objective because Peng has already talked about it. So I'll go straight to my solution. So my solution involved satellite data extraction, feature augmentation, and region-specific processing. For the satellite data extraction, I extracted relevant satellite band values from Earth Engine for each coordinates, the latitude-longitude pair, in the training and test data sets. I then merged these extracted satellite features with the existing features of the provided datasets using the lat-longitude pair. I then, in the modeling phase, I handle each country differently, as we are going to see in the cross-validation section. So my algorithm description. First, as explained, I defined the image collection from Earth Engine by region, ensuring the model uses the relevant satellite images for the given geographic location. I then extract specific Sentinel-2 bands, crucial for understanding features like vegetation and water bodies. Then for each region, I used the reference dates provided in the information page, where for Vietnam it was 2023 April date 16, Spain 2023 April 16, but for Kenya it was for 2023 May the 1st. Then for each coordinate pair, a geometry point is created, and the algorithm it samples the bands at 10 meters. Feature engineering, I created elevation features. Specifically, the one I used was elevation percentile, which provided insights into topographic sensitive models, and then extracted the spectral indices, among them being NDVI, EVI, NDW, and all others. Then all the others provided here. And then I also extracted structural indices like SR, GCI, and CP, CWI, MSI, and MDI. And for the modeling, I split the data into folds. I used stratified key fold, allowing for both and for each individual country. So for each individual country, I had like 10 stratified key folds, and each country was evaluated individually. Model selection, I experimented with LightGBM, XGBoost, and CutBoost, all graded boosting decision trees. And at last, I settled only with one single CutBoost model because it performed the best. There was no need for ensembling. For model training and validation, I trained the selected model on the training data, and the feature engineered features explained the structural indices, the elevation features, and also the vegetation indices, and evaluated the performance on the validation data for each fold, capturing the accuracy. And then for each fold, I aggregated the predictions and used mode or median for the ensemble for the in-folds predictions. So this was the everything before here was the competition of what the competition wanted from us. But after the competition ended, we were tasked to generate biweekly predictions for the whole 2023. And so for the biweekly satellite data preparation for the test regions for the whole of 2023, I used all the dates given. I filtered all the dates given in the Google Earth engine, and used all those biweekly dates to extract the same features that were used in the modeling phase, in the competition phase. And then, satellite data retrieved the bands. Aggregation, I just repeated the same procedure that I used for modeling in the first phase, but now for the whole of 2023 to generate the annual biweekly predictions. So how, after extracting the features and the data, I used the train model in the competition phase to aggregate the biweekly data sets and generate predictions for each time-stamped spectral data instance. And then for the map generation, I generated a prediction map indicating the plastic cover distribution for each test coordinate for each 15-day period, resulting in a time series of plastic cover maps throughout the 2023 region. Conclusion, the data preparation and modeling approach provides valuable insights into agricultural plastic cover distribution across multiple regions. The generated maps can be used to understand plastic usage patterns and inform policy decisions for sustainable agricultural practices. I have not, I forgot to attach the metrics for the competition, but it was above 97% accuracy for both in-fold cross-validation and the competition leaderboard, both the public and the private leaderboard. And this is the end of my presentation. Thank you.
Thank you, Stephen. Good work. Okay, please stop sharing your screen, and then let's invite the second solution for this challenge to talk their submissions. Dami, are you here?
Oh my God, I think I'm muted. Sorry.
Okay, go ahead. Floor is yours.
All right, thank you. Sharing my screen. Stephen, not Stephen. Thank you. Can you see my screen? Just to confirm.
Yes, go ahead.
Okay, excellent. Good day, everyone. I will be presenting my solution for this competition. Just give me 1 second. Screen stop. So I'm not going to go into the background because that's well covered. But just to give a bit of, should I say, backstory to the data set. So we're provided with tabular data as well as access to satellite imagery. And at the start of this competition, I decided, which of these two modes of data or what sort of combination or hybrid of this data set would, give the best result. And of all my several explorations, I found that the tabular dataset gave the highest performing model. And let's bear in mind that the highest performing or the highest scoring model in the competition is not necessarily the most practically applicable model. So with that said, the data is spread across 3 regions in Kenya, Vietnam, and Spain, and constituting a total of about 2,800 data points. The data collected from Sentinel-1 and Sentinel-2 data sets. So my process was pretty simple. First, consolidate the data from the different regions into one data set and explore the data to identify useful features to use in modeling, perform some feature engineering, feature selection, modeling and inference. And in my experience in this competition, there was, a need to review the models eventually and reflect on what was learned along the way. So after consolidating the features, I wanted to get one model that generalizes across the 3 different locations. However, the range of values in each location were, should I say, kind of different and overlapping. So, for example, looking at the image in front of you, you'd see that Vietnam had range of values for some of the variables that coincided with positive values in Kenya. So I needed to engineer additional features that would get rid of that overlapping effect across locations. And also there were highly correlated features across the different 2 data sources. So to, should I say, expand on the features and enrich information more, I computed spectral indices, specifically the plastic index that would help with detection of plastics even more. I computed NDVI and NDWI to enable the model differentiates between vegetation and water, as well as the bare soil index. And I also looked at features that could enhance grayness, polarization for structural information, looked at ratio differences, and also looked at spatial lags. Speaking of spatial lag, the reason I came to that was because I looked at spatial autocorrelation to understand if there are clusters of plastic use in specific regions, and the Moran's I value, I can't recall at this moment, shows that there's strong spatial dependencies, indicating that plastic use is not random or form clusters. So to capture this pattern, I engineered features looking at geohashing or k-means clustering to group regions with similar characteristics. And after feature engineering, I ended up with about 44 features, and I used recursive feature elimination to iteratively remove the least important features. At the end of the day, I had 21 features going into my final model. Finally, my model architecture was rather simple. I used a stacking classifier that includes that stacks of a k nearest neighbors classifier, and that is there to explore the spatial relationship explicitly using spatial lag of the target variable. And then the second stack included a voting classifier that included the mix of random forest, gradient boosting like GBM and cat boost. And this gave a cross-validation score of 0.977, leaderboard score of 0.98, and private leaderboard of 0.979. So to wrap it up, like I said, initially I had to decide whether to go with satellite imagery or tabular data. And eventually I went with the tabular data because it helped to optimize on the leaderboard. However, while exploring satellite imagery, I came across a number of inconsistencies and annotation accuracies, and more than 30 label errors in the train and test set. There were cloud corrupted images as well. While I did address these images and resulted in a much more accurate model, this did not translate well on the leaderboard, as these inconsistencies were also in the test set. But however, I found that this model would have been a better and much more practical one. And finally, to generate a spatial distribution, I found it very computationally intensive. So what I have done instead is to use the CNN model to predict at 500-meter resolution, which is the resolution that a 50 by 50 tile would cover. And with this idea, generate 500 resolution spatial distribution for the entire year. That is planned for next steps, and hopefully when I get that done, I will share the results publicly as well. Thank you very much.
Okay, Dami. So it's a good solution for us that you have done some good work about using satellite images to identify the plastic covers. So up to now, after this joining this challenge, what do you think about the remote sensing technology for the agricultural plastic cover mappings? And do you think in the future, what can we do for that to improve your current solutions?
That's a great question. In the process of this competition, I did a lot of review. There were several research already done on this, and a lot of them include using more visual approaches, and maybe going even a bit more granular, treating this not just as a image classification, but rather as image segmentation. And I think there's opportunities there to explore and perhaps expand to create this, should I say, fine-grained spatial distribution data set that you're trying to achieve out of this in a much more computationally efficient way. So perhaps future development, at least from my end, will be to look into how to generate, a curated data set for, perhaps future image segmentation to should I say, just speed up this process, essentially.
Okay, and I see in your next steps, you say you want to use 500-meter resolution imageries to generate plastic cover distribution maps. So you know that the scale of 500 meter and 10 meters are different. So what do you think will be the challenge of the low resolution mapping for plastic cover if you use that images?
Well, the reason for selecting 500 meters rather, is due to the nature of the of the image data set that I generated, I only have, should I say, class labels per image, right? And so doing it this way is more of a convenience. But assuming I had like an image mask, then generating this distribution at 10-meter resolution is very much possible. So with that said, the limitation of this is extracting image tiles at 50 by 50 would sometimes result in, having, how do I describe this? Let me backtrack a bit. So I have 50 by 50 image tiles where the location for those, where the location for extraction is right at the center of the image. And there are instances where there may not be plastic cover at the center of the image, but there are, plastic covers towards the extremities of the image, right? And what you end up with is a model that would aggregate, plastic use over that, spatial extent into one value. So you will lose information. And, probabilities may be representative of the fraction of plastic covers within each image. So yes, there is a loss of information that would happen if you aggregate at that large resolution. And to mitigate that, like I said, I'm already envisioning this as an image segmentation problem, that allows to should I say, maximize the potentials of vision-based approach while, keeping the classification at a much more granular level, specifically at 10-meter resolution.
Okay, thank you for your
Thank you.
solutions.
Thank you. I have a curiosity, so I want to understand Stephen and Dami where they are based and what they are doing in their life. Very quickly, because we have only 2 minutes.
Pardon me, could you repeat that?
Yeah, Stephen and Dami, where are you based? So where you live, and what are you doing in your life?
Okay. I'm Dami. I'm actually from Lagos, Nigeria, but I live in Winnipeg, Manitoba. That's right at the middle, right at the center of Canada. I have a background in architecture and urban design, and recently changed careers to geospatial machine learning. And I work with the province of Manitoba as an applied scientist.
Okay, thank you, thank you. And Stephen, what about you?
My name is Steven. I'm from Kenya. I have a background in computer science undergrad, and I'm currently working as an AI engineer.
Okay, so congratulations to the two of you. Very, very good, also very good presentations. So I want to congratulate with you. And I want just to ask, thank you. What about the last presenter? We don't have the last presenter, correct?
Yes, I think he doesn't join us, so we just have these 2 presentations.
Okay.
I do know the last presenter is a friend, and I know he's somewhere stuck in Lagos traffic and trying to get home as soon as possible to join us. So perhaps
Yeah, but unfortunately, you will miss the presentation. Okay, thank you. And let's go now to the next challenge. So let me call now Lorenzo Vita and Yixing Mao from UNODC. So they will lead this session on clandestine runways detection in the Peruvian Amazonian Basin challenge. They will make an introductory remark about the challenge, and then they will invite the top 3 teams to describe their solution. This session, again, Lorenzo and Hishin will last for 25 minutes, but now the floor is yours.
Thank you, Maria. And thanks to everyone. I try to make it short, and I'm sharing now the screen with my presentation. and probably I have to swap this, and then you have to let me know whether you can see. It's I'm Lorenzo Vita, Geospatial Information Officer at the United Nations Office on Drugs and Crime, and here goes my colleague Yishin, who really take care of reviewing of all the proposal and the submission of the challenge. The challenge was about the automated detection of illegal runways in the Peruvian Amazonian basin. And also, I want to thank my colleague Jorge Caballero, working in our office in Peru, to provide all the data set and take care about the AOI and training data sets. So clandestine runways, they represent a threat for both security and environment. They are always hidden in the forest, in remote area, difficult to access, and they serve as a pivotal infrastructure for many illegal activities, including, of course, drug smuggling, illegal mining, logging, etc. So they usually are created by clearing the forest for long tracks, and they, of course, they are a starter for forest degradation and deforestation, not just for the runways itself, but also for the activity, illegal activity related to those. So we are carrying out research on this phenomena, and usually we want to look at the spatial distribution and the impact of these runways, also over time. You can see here one that is at the bottom left, associated to mining sites, for instance. And for the time being, we are using mostly visual interpretation, and they are validated through counterparts, air force, etc. But so we are looking into a way to automate the process and create early alert that will be beneficial to really tackle the problem and for decision maker to really act based on evidence. So what we asked to the participant was to use open source imagery, high resolution. So probably, well, we indicated Sentinel. Of course, they could also have used other solution, and possibly with integrating optical and SAR data. So the area was the Peruvian Amazon basin, as said before, and data sources, we have provided some training and testing data sets with runways that were detected and validated and active in a certain period of time. The year when the runways were active was provided with the data set. And finally, also we provided an area of interest to test the model and to see how many runways could be detected. So the outcome of the challenge, we had 387 enrolled, 26 active participants, and 14 with a complete score for public and private, but only 5 of them submitted the full model with report attached, etc. And among those, we decided to top 3 were evaluated to be third is Prashant Kumar Singh, on the name that is a bit difficult to read out. And then the team Terra Pools, composed by Pascal Fortin and Shruti Mukhtria, and the team Da, which was Dami Akini. But what I see now in so among the participants, I only see the Terra Pools team part component.
No, Dami is also here. Dami already
Dami
presented
is
also
here
the
because
first
I
one.
cannot see there. Okay, Dami is here. Okay, so if Dami is here, and then Prashant is Prashant here?
Yes, I'm here.
Okay, because he had probably different name. Okay, so let's start then from the third classified. So Prashant, and I will stop sharing and give the floor to you. And congratulations, of course.
Thank you. I'll just share my screen.
And Prashant, I recall you that you have 7 minutes, but I would like also if you spend some words in the beginning saying where you are, what you are doing. So introducing yourself.
Sure, yeah. Is my screen visible?
We can see it, but it's not in full presentation mode. If you could show the slide only. Thank you.
Yep.
Yep, looks good.
Just give me 1 second. Okay. Yeah, so hi, I'm Prashant Singh. I'm currently pursuing my bachelor's in science from IIT Madras. I'm currently in India. I belong to a small town called Jabalpur in India, from Madhya Pradesh. And yeah, so this is essentially my solution for this competition, runway detection. I'll start with background. I think background has already been given. There's enough context about this competition, so I'll skip this part and directly jump over to data part. So in the training data, as we said, we had some annotated images or some annotated data for already detected runways and the year of detection in which they were detected for the first time. And so these annotations were in line string format, and we had to use it in a model. Then for test data, we had essentially a grid, and we had to run all the predictions on the grid and present all the pixels where we had detected a runway, and as a binary mask, 0-1 predictions. Then apart from the training data which we got, I also used the New York Times Brazil illegal airships data, which is available in GitHub. It had the centroids of the detected illegal runways, and I used this along with the training data which we got. Then coming to data pre-processing, this is essentially where I spent most of my time. So I was most comfortable with RGB band values and RGB images, so I used that instead of all other bands of Sentinel-2 satellite imagery. I gathered around 4 to 5 images per location across multiple months of the year, so that I get like varied images for a certain site, because these are very short-lived runways. So on some months they are available, some months they are not. In some months there is cloud over the region, so sometimes it's not available. So I use like multiple images across multiple months across the full year. Then I removed images which had very high cloud cover, using a very basic detection of pixel counting, essentially pixels which have very high white pixels. Images which have very high white pixels, I'll just remove them completely from consideration. Then increase the brightness, basic contrast correction for the images which were collected. Then for annotations, I use slightly different approach. So first one was for the data set which we were provided, the training data set, which was essentially line strings. I buffered those line strings around 30 to 40 meters and converted them into polygon. And I also used the SAM model to generate automated mask for the regions which we were provided essentially. So the line string and generate random points on those line strings and provide that as an input to SAM and generate the mask for the particular runway. Then after that, I combined both of these polygons, the polygons from SAM and polygons from which I created after buffer. Did an intersection of these two polygons, and then there was some issues with some of the images. Some of the detections were not very good from SAM, or the buffer was just too big or too small in some of those images. So I corrected those manually and created a initial data set for further use. Then after that, on the data set which I created after manually reviewing it, I trained another YOLO V1, YOLO 11 model, V11 model, just on the images which I was sure about that this segmentation is correct. And I also used SAM model again on the images from New York Times. So SAM model I used by giving the input of the centroid of that particular runway, and YOLO V11, which I trained on the data set which I created before. So I used both of these again, intersection of the polygons generated from both of them, manually reviewed the data after that. And after this, I had like the training images, the training data which we got, and plus the annotated images from NYT dataset. I combined both of them, split them into train and test. I did some augmentation on the train part. Augmentations were very simple because this is with satellite imagery, so we could rotate it here and there, do some shear operations, random flips, and increase and decrease the brightness. Just these augmentation, nothing too major on it. So this way I created my train set and test set for the model training. This is from the data set, and then for the test part, it's very simple. So the grids which we got, I created two set of images for each grid. One is essentially the subdivided images, subgrids for each of the bigger grids, bigger grid which we got, and the other was like a full resolution image for the full complete grid. The sub grids were essentially 100 by I divided them into 100 across length and 100 across width part. And then again, the same approach, gather multiple images for a particular location across multiple months, remove all the images which have very high cloud cover, do some contrast and brightness correction, and essentially the image is ready for prediction. Then coming to the modeling part, I did very simple modeling. I went with, again, I used YOLO V11 before and the augmentation and the annotation creation step. And then here also I used YOLO V11. I think most of people would be aware of YOLO 11. It's essentially a state-of-the-art model for object detection, and also nowadays also for segmentation. Task also has both heads for object detection and segmentation. It's considered really fast, but not very accurate, but still good enough to do most of the tasks. Yeah, so my modeling strategy was twofold. I trained the first model on the subgrids which I created, and of course the annotations. I divided those annotations according to the grid which I created, and another model which was essentially a full image of the grid. The idea behind that was there was some roads, some river networks, which the smaller model was getting confused in. There was some what do you call it? Incorrect predictions on the river bank, or consider some of the roads which were like if you show only subset of the image, it will consider that as a runway because it has very close features with the actual runway itself. So the idea was if we do a like large image, you can generalize better. You can look at the network of the road and get a better idea of what actually is a road and what is essentially a runway. So the features would be different. Road would be a continuous contour in the image, and the runway would be a small a small area and small quantum. So that worked really well for me. And finally, after the predictions across all the images, I did intersection of all the images and both the model. And yeah, so augmentation and then training parameters very basic. There was nothing extremely specific. I spent most of the time on the data part, and these were essentially my strategy for model and data. Then there are a couple of things which I tried and which did
Dragan,
not.
sorry. So we are running a bit late.
Okay, yeah.
Could you
This
please?
is my last slide. Yeah, I'll just conclude.
Thank you.
Yeah.
Sorry.
So these are things which I tried. Essentially, I tried using digital elevation model, which didn't work because of the lack of resolutions in the data, and then OSM road network data that also didn't work. And from modeling side, I tried better models, but the cost of the models did not outweigh the YOLO 11 speed, which would get me better iterations in model. Yeah, since we are running out of time, this is essentially my solution.
Thanks very much, and good job. I think it was pretty difficult challenge, this one, I have to say. So without wasting more time, I will give the floor to Terra Pools. We have both Pascal and Shruti here with us. So please, floor is yours, and yeah, congratulations.
But can you see my screen?
Yes, we do.
Okay,
and please, no more than 7 minutes because we are running late.
Yep. Well, thank you for having us today. My name is Pascal, and I will be presenting on behalf of our team. This is the agenda for the presentation. A few words about our team. We are both mid-career professionals transitioning into the climate sector. We're both in the US. Shruti is in California, and I am in Arizona. We met earlier this year during the climate-based fellowship program, where we did an independent study looking at geospatial foundation models with application in climate. After doing a summer school from Climate Change AI, we wanted to get real-world experience working on a GEO-AI project, and we joined that data challenge. So moving on to our solution, first, data processing. We also used Sentinel-1 radar and Sentinel-2 multispectral satellite data for this project. We spent a great deal of time looking at the Sentinel-2 data. As you can see, those three satellite images are the same area. The image in the background on the right, as you can see, it's very challenging to work in this region of the world because of cloud conditions. So we tested different techniques to mask clouds and cloud shadows. We ended up using Google library on Google Engine. And so we ended up masking individual Sentinel-2 data, and we combined images for a full year to generate a composite image to make sure we had the cloud-free images. We did that both for the training of the model and for inference. Although the Sentinel-1 data are not impacted by clouds, we use the same time intervals to generate a composite image, and we merged those on Google Earth Engine. And so the net result is a final image, including 9 different channels, 3 from Sentinel-1 and 6 from Sentinel-2. Now about the model selection and the training. In our case, for simplicity, we used the UNet model, which is widely used for semantic segmentation tasks. As a first step, we use only the RGB channels and decided to use a ResNet 50 encoder with pre-trained weights. The idea was to look at this model and see if it could at least produce reasonable results. Our model was configured to accept additional channels. In the end, we ended up using all 3 RGB channels, as well as the near-infrared channel from Sentinel-2 and 1 VV band from the Sentinel-1 SAR satellite. So we had 5 different channels in the model. The output of the model is an image where the pixel values are either 0 for background or 1 for the runway. Our model was trained on Google Colab using a GPU. Pairs of Sentinel images and masks were created, similar to what was presented just before us. Here's an example of a Sentinel-2 image. The runway is right here, and this is the mask. We also used a line string and created a buffer around the line string. We tested different buffer widths and ended up using a 20-meter buffer, so a runway which is about 40-meter wide, which corresponds to what we can see in the Sentinel data. Let's talk about post-processing. So the model is very good at detecting runways, but unfortunately, it also detects narrow sections of exposed soil. In other words, the model can also detect dirt road segments. So the image on the left shows a number of structures that are connected by a network of dirt roads. There are no runways in this particular image. On the right, you see the output from the model, and you can see that the model detects 5 runways. So how do we minimize the false positive? Due to time constraints, we were not able to either modify or change the model or even expand the training set. We decided instead to use a 2-step process where we use principal component analysis, PCA, to process the individual clusters of pixels. We use 2-component PCA to determine the length and the width of the clusters, and using cuts that were optimized on the training set, so a cut on length and width, we were able to eliminate a large fraction of clusters that were either too short, less than 350 meters, so it cannot be a runway, or clusters with significant curvature. And remember that runways are straight and narrow. Finally, the second step of the process to eliminate roads was to download for each area of interest OpenStreetMap data. And so a detected runway that intersects with a known road was automatically rejected. So the final list of runway candidates was saved to a file and submitted to Zindi for scoring. So this concludes the summary of our solution.
1 minute, Pascal, please. One last minute.
Yes, let me jump to the conclusions. So this is a very interesting project. We learned a lot and are thankful for the opportunity to work on this important problem. Lessons learned, I mentioned that we spent a great deal of time looking at the Sentinel data, in particular the Sentinel-2. And as shown in the first presentation by Lorenzo, we made a lot of time-lapse animations looking at specific regions, and we realized that runways are developed very quickly, sometimes in a matter of weeks. And we didn't have time to investigate this, but we believe that using SAR data could be very useful for monitoring change in vegetation on very short timescales, maybe monthly, and we could detect those runways in the early stage of development. Finally, we want to acknowledge contributions from 3 of our other climate-based fellows, Liang Chow, Dylan Manchester, and Vincent Guzman, for providing valuable comments during this project and for many, many discussions on the role of AI in the fight against climate change. And that concludes my presentation. Thank you.
Thank you so much, Pascal, and congratulations. And also, I want to praise because, well, you are second, both you, of course, and Shruti, but you are the only one that combined the synthetic aperture radar data. So, yeah, thank you. And I don't want to, since we have to run now, we go immediately to Dami, the DA team, who won this competition. So floor is yours, and yeah, congratulations again.
Thank you. For a second, I thought I was talking to myself again. So this is my solution to this competition. I will be skipping a lot of initial slides because a lot of it has really been covered. and perhaps focus more on things I did differently. And just a bit of a recap, we were provided with shapefiles that had line strings for detected runways. And for me personally, at first, I was a bit confused about, what certain variables meant and how to begin to query this temporal dynamic of the runways. Eventually, to download my data, I had to think about, I had to make certain assumptions that I'll, describe down the line. As previously explained, the test set provided for this challenge covered a large expanse of about, 1,500, I think 15,400, meters by 15,270. So the idea was, at what resolution would I be able to work to minimize computational overheads, because computational resources is quite limited at my end. So the idea was to break this down into, should I say, more manageable steps and sizes. And as many of the other participants did, I took a sliding window approach to inference. And with the sliding window approach, there's a chance for misclassifying or misidentifying runways. So to combat this, I took a localization approach and then a segmentation approach. At first, within every slice of the test region, first of all, classify if there's a runway there or not, and if there's a runway, segment it. And in order to download the data, the main assumption I made is that all runways are active in the year of reference specified in the data provided. And that helped with, that really helped with narrowing down temporal range for data collection. So my data source is primarily from Sentinel-2. I considered Sentinel-1 SAR images at first, but for ease of data management, I stayed with Sentinel-2. In order to decide what channels to go with, I spent time combining different bands on Copernicus browser, and eventually found that the RGB channels, the near infrared and the shortwave infrared bands gave the best features to identify runways. And more importantly, I wanted images that were not cloud covered. So in the data download step, I ensured that images that were, I only downloaded images that had less than 10% cloud cover.
Yami, sorry to bother you, but yeah, 2 minutes for you.
2 minutes left? Oh
I'm sorry, because we are running late. I've been
Okay.
told to be strict on that.
Okay. Sorry. Like everybody else, I buffered and rasterized images. Since I took a segmentation approach, I wanted segmentation masked and corresponding images. What I also did differently was to get negative samples, samples where there were no runways, in order to help the model generalize better. I had about 150 runway images and 150 non-runway images. This is an example of what my dataset looked like. They were about 256 by 256. And then I computed additional spectral indices, including NDVI, moisture indices, to help the model understand where water was and where there's greenery. And finally, I added data augmentation, random flip, contrast, like everybody else. And what I also did differently was to generate artificial road paths, because as previously mentioned, the model was detecting roads. So during the data augmentation and training, I added dynamic road paths at every time during data loading. My model was very simple. I used a dual classifier segmentation model by modifying segformer model, which essentially is one of the state-of-the-art models for image segmentation. I did try vanilla UNet that gave good results as well, but I opted for segformer just to squeeze the accuracy on the leaderboard. So I added in the year of detection, potentially to support, temporal variables down the line, and then concatenated embeddings from images and temporal variable, and then pass this concatenated embeddings to the seg format head and the classifier head. On the left is an example of what the model output looks like. The validation metrics were great. And then I performed the sliding window inference as previously mentioned. And what I noticed was that the model's raw outputs were really good at detecting runways. There were a couple of missed detections along the way, but mostly good detections. And finally, the raw outputs were binary masks, and I wanted, much more practical use. So eventually, I tried post-processing to remove, to threshold and define runways better, skeletonize and straighten them to have straight runway lines, did binary closing to close gaps, removed small objects that are not representative of runways, and also removed non-linear objects such as curved objects or round ones. Everybody's expressed a lot of the limitations they have, and I had, faced similar ones. For example, lots of cloud cover images, complex backgrounds, resulting in false positives where wide roads are mistaken for runways, and then, deciding, what the active status is. My assumption that that a runway is active in the reference here may not have considered that the temporal dynamics too well, and as such, aggregating over large periods could result in having less distinct runways. So future work, there are other additional data sources provided for this. I will be exploring those. During the course of this, I tried YOLO on this, a newly curated data set from the original data set I worked with. And that gave really, really great score and performance as well. But due to time limitations, because I didn't join this competition till pretty late, I didn't explore, how to translate that into sliding window predictions to yield higher and much more useful results. So that's still work in progress for me. Eventually, I will open source the results from that little exploration eventually. So that's my work.
Thank
We need to
you.
close, Sami. Thank you so much. And yeah, congratulations again. It was very brilliant solution. And just to say, Maria, don't kill me. I want to say that.
Yes,
just to say one thing that sometimes roads are even used for landing by this aircraft. Sorry, over to you, Maria.
Okay, thank you. So thank you, Lorenzo. And yes, unfortunately, we are a bit late. There is no time. So I will give immediately the word to Francesco for the last challenge. So Francesco, please, 4 minutes for you, 7 minutes for the other, because if not, we will be cut and I'm not able to make the ceremony, the final ceremony.
Sure. So we're going to try to finish. So we have really 15 minutes. So I will be very fast because we have to try to finish by 10 minutes before 6. So I think all the teams are here, and I'm going to present very quickly. This was an air quality challenge, and I'm going to share the screen really quickly so that we see what we are talking about. Very trivially, basically, you got information from these stations that measure the NO2 concentration from ARPA, different ARPAs. In Italy, they're the environmental agencies, so they have very accurate measurements, and they have hourly measurements of the air quality at ground level. So the challenge was to use the satellite image information plus any other spatial information that you could collect from satellite or cartography anywhere to create a model that predicts in time and in space the NO2 concentrations. And that was quite well done. There was a lot of teams, a lot of participation, because the importance of being able to map this information, not just at those points, but everywhere in the area, is very, very important. Now, you will notice here that it's only in the north of Italy, there's the mountains. So we only kept the plains, the Pianura Padana, because of course, we tried to keep other factors constant. So we did not include mountainous areas to see if the models, how well the models work here, only in the without the effect of mountains, which of course will also have an effect. And so the people were given data for training and validation, and we kept a blind data set where you have all the predictors with of course the coordinates plus the information, the features for predicting, and you were free to add other features, but you were not given the final measured, observed values. So we used that to calculate some error metrics, and we finalized the 3 winners who I think are here. And I don't know, since I just connected, I don't know if you first define the winners, who is the first, second, third place, Maria, or should we first present and then have them?
Present them, and nothing else.
So let's go for the first presenter. So I'm calling. Sorry, I pronounced your name correctly, Abdul Tash, and I think he will present. So this is mixed. I asked them to present first. So Abdullah, if you can share your screen and start your presentation if you're ready.
Actually, I will present instead of
sorry. Yeah, Batu, you are his teammate, so of course you are.
Yes, he is my teammate. I will share my screen.
And remember to be around no more than 4 or 5 minutes so we can catch up the time. You can think of this as an elevator.
No, 7 minutes, but strictly 7 minutes, no more than that, because if we don't have time. Yes.
Okay. So let's keep on the 7 minutes.
Can you see my screen?
Yes. Team ABBA, I like that.
Yes, Team ABBA, like old Swedish music group, right? Hello everyone, we are Team ABBA, consisting of Abdullah and Batuhan. Today we are excited to present our solution that earned second place in GeoAI ground level estimation challenge. Our approach combines data preprocessing techniques with machine learning methods to accurately estimate surface concentrations using remote sensing data. The aim of the GeoAI ground level NO estimation challenge is develop ML models to estimate surface NO concentrations using only public air remote sensing data. This problem is crucial for air quality monitoring and environmental health. As we can see, here is the data description. And data sample, you can see our data. Let me briefly explain the structure of our data set. Each unique ID represents a specific monitoring station with fixed latitude and longitude coordinates in the Lombardy and Veneto regions. The data set contains daily measurements spanning from 2019 and 2021, giving us a comprehensive temporal coverage, NO2 concentrations, and related parameters. Correlation metrics. One of our steps in the analysis was to examine the relationships between different variables using a correlation matrix. As seen in the correlation matrix, the column with the highest correlation with the target column seems to be an NO2 drop column. this shows us that the NO2 trough column or the features we will produce from the NO2 trough column may be most important features in the model we will create. Our solution have 10 steps. I will describe these steps to you. First, important libraries. We use these libraries for the solution. Loading data sets. The data sets were loaded. Then the data column was checked for any problems. Adding data features. Multiple data and time features are extracted, such as day of the week, month, quarter, and seasonal indicators. Trigonometric transformations are also included to capture cyclical patterns in the time-based data. Filling non-values with iterative imputer. We used iterative imputer for the fill these non-values. Also, there is missing values in the target column of the given data frame. We are fill it using a random forest regressor. Selecting best model. Multiple regression models are evaluated using k-fold cross-validation. XGBoost and LightGBM regressors are trained sorry.
No, you have 2 minutes.
Okay, I will jump these things. We also added shift and MF features. Shift and exponential moving average EMA features are created for specific columns. Also, we added geospatial features, as you can see. Also, we have to optimize our model performance. We used Optuna for the hyperparameter tuning. Final model is an XGBoost model with optimization hyperparameter is trained k-fold cross-validation with story splits. Because XGBoost was best model for this solution. And last, feature importance. 9 of the top 10 most important features were NO2 drop EMA features. And thank you for attention.
Thank you for perfectly staying on time. Great.
Thanks.
So the next stop, please share the screen.
The next team for presentation.
Yeah, I think
Ensar, Engin.
Dilek is connected.
Dilek, yes. Dilek, Engin, your team.
My teammate will present the presentation.
Okay. Where's your teammate? Is Engin?
Engin, yes.
Ah, okay, great.
Okay.
The floor is yours. Remember to be...
I am starting presentation.
Yes, absolutely.
Okay. Hi, I am Engin from Turkey. I am electrical and electronic engineers. I will do the presentation about ground level estimation challenge. Here is my team members. Our problem is to accurately estimate ground level NO2 concentrations.
We can't see your presentation.
You don't see presentation?
No, if you have a presentation,
I
please
didn't share. I didn't
the green button at the bottom of the...
I'm sorry. I'm sorry.
So now you have 6 minutes left. Time is running.
Oh. It is okay now?
Presentation mode, you can.
Okay.
open.
And we deal with geographic and temporal complexities and try to provide a robust and efficient model for real-world implementation. Our solution is basically on 4 parts: exploratory data analysis, feature engineering and feature selection, light GBM model plus a distance-based model, and pseudo labeling. As all the participants know, there are 6 new locations in the test set that are not included in the training sets, and the train and test sets have the same period time. When we plotted this map, we see that some test points are very close to the training points, and some test points are far from the closest training points, and some test points are at moderate distances to training points. So we think to design a distance-based model. A distance-based model is very easy. Identify the k nearest training locations from each test point. Find the distances by using Haversina formula. Then calculate weights by taking inverse of distance between test and training points. We calculated 2 weights, 1 divided by distance. This accounts for weather effects. 1 divided by distance square. This captures the urban effects such as traffic and industrialization. Then take the average of the weight. After, multiply all the training NO2 values with the corresponding weights and sum them to calculate the weighted average. This will be our NO2 prediction of the distance-based model. Then we combine distance-based model with the light GBM. What worked? There are missing values, and forward-backward filling boosts our performance. And we extract the temporal features from date. Also, from domain knowledge, we added attitude data. It has also very good correlation with the target variable. Also, you see here the targets, the independent variables with the independent variables correlation to target variable. There are some variables have good correlation with the with the target variable. That's why we multiplied and divide these variables each other and add cross features. This also boosted the performance. Also, we created mean, standard deviation, max, and rolling statistics of independent variables and moving averages of independent variables. And here you see latitude and longitude distributions of train and test set. You see they don't overlap, they don't fit each other. So if we train the data according to latitude and longitude, it will not give good generalization to test set. That's why we excluded latitude and longitude, and this also makes our model performance increase and helps generalization, boosted the public score. Also, we do hyperparameter tuning Optuna and combine 2 models. As I told before, some points are very close to training points, some test points. So we use only distance-based model results for these points. And some points are far away from the training points. So for these points in the test, we only use light GBM model, and some points are at moderate distances. For these 2 points, we use light GBM plus distance-based model results. After we take the predictions, we labeled the test data with these predictions, and then combine train data and labeled test data, and again give all this data to the light GBM model. This also boosted, this is known as partial labeling technique, and this also boosted our light GBM models performance. Here you see our feature importances. These are cross features and elevation features. These are important time series features. They work well. And what didn't work? We tried lasso, SVR, artificial neural networks, some combinations of them, but they didn't work well. In this competition, to gain insights from spatial analysis and build a distance-based model and combine the results with the light GBM inspired us, that excited us. Here is the architecture diagram. We take the data, ETL process, and feature engineering, as I talked before. We give the data to light GBM model and to distance-based model. Then we ensemble the results and put the results to pseudo labeling model as labeled target. And again, combine the results with the distance model and give the final predictions. Thank you for listening to me. I can answer your questions.
Thank you. Thank you very much. We leave questions if we have time for later. Thank you also for being perfectly on time. So we can move on to the last presentation. So I sent a message because I don't see, I think Onur Kosh, if is presenting. I saw that somebody raised his hand, so I think I cannot, I don't know if I pronounced correctly. Kismet is raised his hand when I sent the message. So I just saying out loud, is Onur Kosh connected online? I don't think so because I did not get any feedback from the chat. So I think he just did not.
Okay, Francesco, if he's not here, don't worry because in any case we are late, so we have the possibility to catch up with the time. So thank you also for this last challenge. And at this point, I want to call, I have to say the most important person here. So now it's time to move to the award ceremony, and I want to call Andrea Manara from the ITU. I have to say that Andrea can be considered the cornerstone of this initiative. So he's the person who connects all the various people here. And I can say without whom this initiative could not move forward. And Andrea, I want really to publicly thank you for your dedication and passion. And thank you from me, and I believe from everyone. And now I give you the floor for the award ceremony.
I thank you very much, Maria, for this too kind introduction. Indeed, a good day all. So it's really a pleasure for me to be here to reward the outstanding contributions from the top teams, but more generally, let me really acknowledge all participants of this 2024 ITU GeoAI competition. In these third editions, I think that we really had a record number of participants. And so I really want to thank anyone for making this competition really a success. I also want to remind you that those challenges are run on the Zindi platform. And I thank Zindi for the fruitful cooperation. And I really hope that we can organize in 2025 always more successful competition. Without further ado, let me move to the award ceremony. So let me share my screen. Okay, this is shared, and then I just want to start.
Andrea, what do you think we can call everyone now?
Yes,
Yes, everyone here for the award ceremony.
Can you just confirm that you can see?
I can see it. It is not in presentation mode. So
it's not in presentation mode. Okay, so
oh, I see two screens. Yeah, display setting.
I swapped.
Yes.
Okay, so
now it's fine.
Everything is fine. Okay, so let's begin with the award for the agriculture plastic cover mapping. So let us call Pengu, the organizer of the competition from FAO. So let's start with the third place. Adeinka Sotunde, I'm really sorry that you were not able to be here at the beginning, but please, if you can switch on the camera and just, you have 1 minute to say something about yourself. If you are here still.
Maybe he's still not here.
Ah, He's not here because I saw him arriving. Okay.
I think his network got disconnected.
Unfortunately, okay. I really hope that that he will participate in next year competition, win another prize, and then I'm looking forward to see his presentation. So now let's move to second place, Dami. So that is you. Really, congratulations. And okay, yeah, I forgot to say that you will also receive a money award, which will be delivered early January. So it will be $200 for the third place, 300 for the second, and then let me call the first place, Stefan. I really want to congratulate you on the winning of this competition. Just, I think that we have a couple of minutes, you, if you want to wrap up the competition with the winners.
Okay, I think I can do a brief summary of for the winners. For this year, we have this topic as we are working on using satellite imagery to identify agricultural plastic covers. It's an important facility for agriculture. So next year, I think we will continue on this topic about agricultural mapping, and we will come back to cropland, but with somehow more difficulties. And that is in the condition that we cannot get training samples and how we can identify the croplands. Basically, for this year, very thanks for all the participants, and really congratulations to all your contributions and your participants. Thank you. Back to you, Andrea.
Thank you very much. And let's move to the second competition, the clandestine runaways detection. I'll call Lorenzo and your colleagues from UNODC, Jorge and Jixin. And I really want to thank you a lot to you and the UNODC for having contributed $1,000 for this competition, so that the first prize is richer, is 1,000, the second 600, and the third 400. So let's move to the winners. So the third place is to Parashant. Thank you very much. Congratulations. The second place. The second place is for Pascal and Shruti. Congratulations.
Thank you.
Very well done. And then the winner is Dami. Congratulations.
Thank you.
I give the floor to Lorenzo, and if you want to have some final words, and also if the winners want to say something, a couple of minutes.
Yeah, thank you, Andrea, and thank you, ITU, for making this possible, and to all participants, especially the three that we really made a great job in this competition on runways that I think was very challenging. We didn't receive so many submissions because many of the participants gave up, but those that provided solution, those that received the award today were very good, I think. So thank you. I don't know. I also thank you, Ishin and Jorge, that helped me out with all this work.
I thank you very much. Lorenzo, let's move to the last competition, NO2 ground level estimation. I will ask Francesco also to be on stage, and let's move to the prizes. So the third classified is the team composed by Engin, Dilek, and Tututke. I'm sorry if I didn't spell well your names. Well done. Congratulations.
Thank you.
The second prize goes to Onur. Congratulations. I'm afraid that is not there. It's not here. And the winner of this competition is our Abdullah and Batuhan.
Thanks so much. Thank you. We are truly honored and proud of this achievement as a team.
Thank you very much. Very well done. So I think that I can stop the sharing of the screen, and we can have some final word. So if you can all switch on the camera, and I'm really very happy of this competition. And if anyone want to say something, we have still 5 minutes. Any of the host or the competitors? Nobody wants to take the floor. So I again, my best congratulations to all of you. I really hope that you will participate again next year in next year competitions, and I wish you an excellent end of the year vacations. And with this, I will give the floor to Anna, and I'll see you next year. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.